Some planets rain shards of molten glass sideways through permanent hurricanes. These are not fantasies but real worlds light years away, and they are forcing us to rewrite the rules for life itself. By the end of this journey, you will know the 25 most bizarre exoplanets that shatter our definition of a habitable world. We will explore a planet made of diamond and another spiraling toward its own doom. What does it truly mean for a world to be alive? 40 light years from Earth, a world made of diamond orbits its star with such frantic speed that an entire year passes in less than a single Earth day. This is 55 Cancri E, a super-Earth whose very composition defies everything we consider normal. Its radius is double that of our own planet, but its density and composition are utterly alien. Scientists believe the planet is overwhelmingly rich in carbon, the same element found in pencil lead, but here, under pressures and temperatures that soar above 2,000 degrees Celsius, that carbon is crushed and forged into a crystalline structure. Vast fields of diamond and graphite likely form a glittering, impossible crust. This is not a stable, rocky world like ours, built on silicates and iron. It is a testament to the violent and diverse processes of planet formation, where a carbon-rich protoplanetary disk gave birth to a jewel of a world. The concept of a habitable zone, that comfortable belt where liquid water can exist, means nothing here. The surface is a scorching hellscape, where any water would instantly vaporize and the very ground beneath your feet would be a fortune of gems. This diamond world forces us to ask a profound question. Is our search for life too narrowly focused on planets that look like our own? Habitability may be less about finding another Earth and more about recognizing the staggering variety of chemistry that the universe can produce. If a world of diamond can exist, what other impossible geologies are waiting to be found? The answer becomes even more extreme as we turn our gaze to a planet where the clouds are not made of water, but of vaporized rock. That serene, deep blue marble hides a truly ferocious nature. 64 light-years away, a planet called HD 189,733b presents a beautiful, Earth-like face to the universe, but this is a fatal illusion. It is a hot Jupiter, a gas giant orbiting perilously close to its star. This proximity locks the world in a gravitational embrace so tight that a year passes in just 2 Earth days, and the stellar radiation bakes its atmosphere to a sweltering 1,000 degrees Celsius. Any notion of water or life is instantly erased. The beautiful blue color does not come from tranquil oceans, but from an atmosphere thick with silicate particles. These are tiny grains of vaporized rock, the same stuff that makes up sand on our beaches. Here, high in the atmosphere, these silicates condense into droplets of molten glass. And then the real horror begins. The planet is scoured by winds that scream across its surface at an unimaginable 8,700 kilometers per hour. That is over 7 times the speed of sound. These supersonic hurricanes do not bring water rain. They whip the molten glass through the air horizontally, creating a permanent, blistering sandblast of razor-sharp shards. This is a world where the very air is a weapon, a fluid, cutting tool that would shred any probe or ship in an instant. Scientists discovered this glass rain by analyzing the starlight filtering through the planet's atmosphere, a technique called spectroscopy. The chemical signature of silicate vapor was unmistakable, painting a picture of an atmospheric cycle more akin to a forge than a weather system. It forces us to confront a harsh truth. A planet can look inviting from a distance, its color reminiscent of our own safe harbor, while its reality is utterly lethal. This expands our understanding of the limits of life, showing that habitability is not just about temperature or water, but about the very nature of the environment itself. If the atmosphere can become a storm of glass, what other invisible dangers might lurk on distant worlds? Our search must now turn to a planet where the danger is not in the air, but in the very structure of its orbit, a world torn between perpetual day and endless night. Gliese 581c presents a cosmic paradox, a world caught between two eternal, brutal extremes. Orbiting a calm red dwarf star just 20 light-years away, this super-Earth sits within the theoretical habitable zone, that region where temperatures could allow for liquid water. But its proximity to its dim star has sealed its fate through a process called tidal locking. The same gravitational forces that give our ocean tides have, over eons, forced this planet to always show the same face to its sun, just as our moon does to Earth. The result is a planetary schism of fire and ice. One hemisphere is a permanent, scorching day, bathed in relentless stellar radiation. Here, temperatures are so high that rock could flow in vast lava seas. The opposite hemisphere is an endless, deep freeze night, where any atmosphere would likely condense and fall as snow, creating a global ice sheet of unimaginable scale. Between these two hellscapes runs a thin ribbon of twilight, the Terminator line. It is here, in this perpetual dawn or dusk, that scientists once speculated conditions could be just right for liquid water and perhaps even life. A sliver of a world balanced on a knife's edge between incineration and absolute zero. Yet this tantalizing possibility crumbles under further scrutiny. Climate models suggest a planet like this would not sustain a stable atmosphere. The staggering temperature difference would create hurricane-force winds roaring from the hot side to the cold, and the atmosphere itself would likely collapse, either freezing out entirely on the dark side or being stripped away by stellar winds. This shatters a key assumption in our search for life. A planet can be in the perfect spot, the Goldilocks zone, and still be utterly uninhabitable due to its fundamental orbital mechanics. Gliese 581c is a stark lesson that location is not everything. It forces us to ask what other subtle factors can render a world sterile. Our search for life must now account for these gravitational traps, where a world is frozen in a single, eternal pose. But what about a planet that is the complete opposite of this dense, locked world? What if a world were so light and fluffy it could defy the very concept of a solid surface? This concept of a solid, tangible world dissolves entirely with Kepler 7b. Here is a gas giant so absurdly lightweight that scientists often compare it to a cosmic puff of air. Located 3,000 light-years away, this world is a paradox of scale. It boasts a radius 1.5 times that of Jupiter, yet it contains only half of Jupiter's mass. The result is a density lower than that of styrofoam. If you could find an ocean large enough, this entire planet would float. Its atmosphere is not a thin layer atop a solid core, but a vast, bloated envelope extending thousands of kilometers into space. This incredible puffiness is its greatest mystery. What force is inflating this world like a hot air balloon? Standard models of gas giants cannot fully explain its structure. The intense heat from its nearby star plays a role, baking the outer layers, but some internal source of heat, perhaps from the slow gravitational contraction of the planet itself, must also be at work, keeping its atmosphere distended and diffuse. The view from space would be dazzling. Observations from the Kepler telescope revealed a stunning anomaly, a brilliantly reflective patch on the planet's sunlit side. These are not ordinary water vapor clouds. They are high-altitude clouds, likely composed of silicates and other minerals, acting like a massive mirror reflecting its star's light back into space. Yet this beautiful, bright facade is a deception. Below those reflective clouds lies a world of extreme heat, with a predicted temperature soaring above 1,500 degrees Celsius on its dayside. There is no solid surface to land on, only a gradual thickening of the atmosphere into a hot, dense fluid state, a crushing, gaseous abyss. Kepler 7b shatters the standard categories for planetary evolution. It proves that gas giants are not all monolithic, heavy worlds. They can be inflated, gossamer things, challenging our very understanding of what makes a planet. This raises a fascinating new avenue in the search for life. While a puffy giant like this is utterly hostile, what about the moons that could orbit it? A large, stable moon tucked at a safe distance could potentially possess liquid water and a stable climate, all while orbiting this bizarre, lightweight primary. Our search for habitable worlds must therefore expand to include the moons of these inflated giants. But the strangeness does not end with single stars and their puffy planets. Let us now journey to a system where a planet orbits not one, but two suns, casting double shadows on a truly alien landscape. Two suns would set in its sky if it had a solid surface to stand on. Kepler 16b is a world of celestial duality, a Saturn-sized gas giant locked in a gravitational dance with not one, but two parent stars, 200 light-years away. This real-life Tatooine proved that planets can form and persist in the complex environment of a binary system. Its one-year orbit takes 229 Earth days, a graceful loop around both of its stellar partners. This creates an environment of profound instability, where the amount of stellar radiation bombarding the planet changes constantly as the stars themselves orbit one another. The climate would be a study in violent swings, with temperatures fluctuating wildly as the planet moves closer to one star, then the other, or finds itself in a period of double daylight. This constant shifting challenges the very foundation of a stable, life-friendly environment. While Kepler 16b itself is an uninhabitable gas giant, its profound implication lies in the possibility of moons. A large, rocky moon orbiting this giant could, in theory, reside within the system's habitable zone, but life on such a moon would face extraordinary challenges. The tidal forces from both the planet and the two stars would be immense, potentially triggering intense volcanic activity, turning the moon's surface into a cracked and molten landscape. The light cycle would be unpredictable, with days of single sunlight, double sunlight, and even periods of darkness, all dictated by the complex celestial choreography. This forces us to expand our definition of a stable orbit. It is not merely a clean circle around a single star, but a delicate balance within a system of competing gravitational pulls. Kepler 16b shows us that life, if it were to arise in such a place, would have to be incredibly resilient, adapted to a world of constant, radical change. Yet, even this dynamic system seems stable compared to a planet that is not just changing, but actively disintegrating, vanishing before our very eyes. While some worlds are inflated or locked in place, others are actively vanishing. HD 209458b, nicknamed Osiris, is a world in the process of unraveling. 150 light-years away, this hot Jupiter orbits so close to its star that its atmosphere is boiling away into the void of space. The star's intense radiation superheats the planet's hydrogen, blasting it away at speeds of over 35,000 kilometers per hour. This creates a vast, comet-like tail of gas that streams behind the planet for millions of kilometers. It was the first world where astronomers directly observed this phenomenon, a discovery made by the Hubble Space Telescope. The telescope did not see the tail itself, but instead detected the telltale signature of the evaporating hydrogen gas as it blocked a tiny fraction of the star's ultraviolet light during each orbit. This is not a slow leak, but a planetary hemorrhage. Scientists estimate Osiris is losing over 10,000 tons of hydrogen every single second. At this staggering rate, the entire gaseous envelope could be stripped away over billions of years, potentially leaving behind nothing but a scorched, barren core. This evaporation shatters our ideas of planetary stability. We often think of planets as permanent fixtures, but Osiris shows they can be transient, their atmospheres fragile shields in a hostile cosmos. This raises a chilling question for planets orbiting volatile red dwarf stars. If a giant planet like this can be stripped bare, what hope does a smaller, rocky world have? The relentless stellar winds from such stars could scour away the atmospheres of any Earth-like worlds in their habitable zones, leaving them as airless, irradiated rocks. Osiris is a stark monument to the destructive power of a star, a world living on borrowed time. But what about a world with the opposite problem, a planet that is not losing its volatile elements, but is completely drowned in them? Our search for life now plunges into the depths of a global, endless ocean. 48 light-years away, a world cloaked in perpetual steam offers a different kind of ocean. GJ1214b is a super-Earth, a class of planet larger than our own but smaller than Neptune, and its true nature has puzzled astronomers since its discovery. Its radius is about 2.5 times that of Earth, but its mass is nearly 7 times greater, leading to a startlingly low density. This is not a dense, rocky world like ours. The numbers point to a composition rich in something far less solid, something that covers our own world but here exists in overwhelming abundance: water. Scientists hypothesize that GJ1214b could be a true water world, a planet completely engulfed by a global ocean hundreds of kilometers deep. This is not an ocean as we know it. The surface temperature soars to around 200 degrees Celsius, and the pressure from the immense depth of water would be crushing. Under these extreme conditions, water enters an exotic state known as a supercritical fluid. It is neither a true liquid nor a gas, but a searing, dense substance that can dissolve materials like a liquid while flowing through solids like a gas. Deeper still, where pressures become millions of times greater than at the bottom of our Mariana Trench, the water could be compressed into strange, hot crystalline structures, forms of ice that remain solid even at hundreds of degrees. This world shatters the simple equation of water equals life. Here, the very substance we search for becomes a hostile medium. There are no continents, no shorelines, no shallow seas where life could easily gain a foothold. The entire planetary surface is an abyssal plain, a crushing, dark, and hot expanse. Scientists have tried to peer into its atmosphere using transmission spectroscopy, analyzing the starlight that filters through its air. The results are a uniform, featureless haze, suggesting a thick, steamy atmosphere possibly rich in hydrogen, further obscuring the mysteries below. How could life exist in such a place? Any biology would have to thrive in total darkness, under unimaginable pressure, potentially relying on chemical energy from hydrothermal vents on a submerged seafloor. It would be a life utterly alien, divorced from the sun, navigating a world with no up or down, only endless hot fluid. This aquatic enigma forces us to reconsider the most basic ingredient for life. Water is essential, but its context is everything. A global ocean may not be a cradle for life, but a scalding, lightless prison. And just as we grapple with a world defined by its unbroken ocean, we must turn to a planet whose climate is defined by its wildly broken orbit, a world of fire and ice in a relentless, chaotic cycle. HD 80606b endures the most violent seasonal shifts imaginable. This gas giant, 190 light-years away, does not travel on a gentle, circular path. Its orbit is a highly eccentric ellipse, a dramatic slingshot that sends it from the frozen depths of its solar system to a blistering close encounter with its star. At its farthest point, the apastron, the planet is a frigid world colder than Pluto. Then it begins its plunge inward. As it approaches its closest point, the periastron, the star's gravitational pull accelerates it, and the surface temperature skyrockets. In a matter of just a few hours, the global temperature can increase by over 500 degrees Celsius. This is a summer hotter than the surface of Mercury, achieved with a speed that defies any earthly concept of seasonal change. The atmospheric consequences are apocalyptic. The sudden, intense heating does not spread evenly. It superheats one hemisphere, creating a thermal shockwave that triggers supersonic winds, screaming across the planet at thousands of kilometers per hour. These winds are not gentle breezes but global firestorms, redistributing the immense thermal energy and likely spawning hurricane systems larger than entire planets. For a brief, terrifying period, this world becomes a cauldron of unimaginable violence, a climate in constant, furious upheaval. This bizarre orbit challenges a core assumption in planetary science, that stable, circular orbits are a prerequisite for any form of habitability. While HD 80606b itself is a hellish gas giant, the implications for any large moon orbiting it are profound. Such a moon would experience periodic, extreme thaws. A frozen surface could momentarily liquefy, only to refreeze just as quickly as the planet swung back out into the cold. Could life, in some incredibly resilient form, emerge in these brief windows of opportunity, hibernating through the long, deep freeze? It forces us to consider that habitability might not be a permanent state, but a cyclical phenomenon, a fleeting moment of grace in an otherwise hostile cycle. This world of extreme seasons shows that climate can be a roller coaster, not a steady condition. Yet, even the wild temperature swings of HD 80606b are not the ultimate expression of a star's influence. What happens when a planet absorbs nearly all of the light that falls upon it, becoming a shadow in the cosmos? In a cosmos filled with radiant worlds, TRS-2b stands as a void. This gas giant, orbiting a star 750 light-years away, holds the ominous title of the darkest planet ever discovered. It reflects less than 1% of the light that strikes it, making it blacker than coal and darker than any object in our own solar system. Even fresh asphalt reflects more light than this alien world. It is a Jupiter-sized planet, but one that has been baked by its extreme proximity to its star, with a surface temperature soaring above 900 degrees Celsius. Yet, despite this intense heat, its atmosphere is eerily devoid of the bright, reflective clouds that make Jupiter and Venus shine so brilliantly in our sky. Instead, its air is a soup of mysterious compounds, chemicals like vaporized sodium and potassium, or perhaps even complex organic molecules like gaseous titanium oxide. These substances do not scatter light, they devour it. The planet is a light trap, an abyss in space that swallows nearly every photon that dares to enter its atmosphere. This profound darkness forces a complete rethinking of planetary albedo, which is simply the scientific term for how reflective a world is. Our models of atmospheric chemistry struggle to explain a world that is so efficient at absorbing light. It suggests that some planets might be virtually invisible in the spectrum of visible light, detectable only by the faint infrared glow of their own immense heat or the subtle dimming they cause as they transit across their star. How does this absolute blackness affect the planet itself? The energy balance is wildly skewed. With almost no sunlight reflected back into space, nearly all the stellar radiation is absorbed, contributing to the planet's scorching temperatures and potentially fueling violent, permanent storms deep within its lightless atmosphere. For any potential life, the implications are bleak. The surface, if there is one deep within the gas layers, would be a place of absolute, unending blackness, hotter than a furnace, with no visible star in the sky, only a perpetual, starless night. This dark enigma shows us that a planet can be physically massive yet remain a shadow, a ghost in the celestial machinery. And just as we contemplate a world that absorbs all light, we must now turn to one that does the opposite, a world so new to the universe it is still glowing with the fierce heat of its own violent birth. Deep within the cosmic nursery of a binary system, a newborn giant glows with the residual heat of its creation. 2M127b is not a mature, stable world, but a planet caught in its own infancy, a colossal body several times more massive than Jupiter. It orbits not a true star, but a brown dwarf, a failed star too small to ignite sustained nuclear fusion. This entire system is a mere toddler in cosmic terms, and at 170 light-years away, it offers a rare, direct portrait of a planet's violent early years. The view from a nearby vantage point would be surreal. The brown dwarf primary would cast a dim, ruddy light, while the planet itself would shine with an intense magenta glow, radiating the immense heat from its recent gravitational collapse. This is a world still cooling down, its surface temperature a searing 1,600 degrees Celsius. Its environment is one of chaos, potentially still surrounded by a disk of leftover dust and gas, the raw materials of its own formation. For scientists, this direct image is a gold mine. It challenges the dominant core accretion model of planet formation, which suggests gas giants form slowly from a solid core that then accumulates gas. The immense distance between 2M127b and its brown dwarf is difficult to explain under this model, hinting that some giants may form more like stars do, through the direct gravitational collapse of a gas cloud. This youthful giant forces us to ask a profound question about the potential for life in such a system. Could a moon form around this behemoth, and if so, what would its existence be like? The environment would be bathed in intense infrared radiation from the hot planet, while stellar winds from the brown dwarf could strip away any nascent atmosphere. The moon's surface might be a constantly shifting landscape of volcanic activity, fueled by the intense gravitational tides of its massive parent. Habitability here is not a present condition, but a distant possibility, something that might emerge only after billions of years of cooling and stabilization. This young world teaches us that a planet's potential is not fixed at birth, but evolves over eons. Our own solar system was once a similarly chaotic place, and seeing 2M127b is like looking back in time at Jupiter's own fiery childhood. This glimpse into planetary infancy makes the next world seem even more frantic, a place where time itself is accelerated to a dizzying speed. Its orbit is a tightening noose. WASP-18b is a gas giant 400 light-years away, living on borrowed time. This planet is a hot Jupiter of immense proportions, 10 times the mass of our own Jupiter, and it is locked in a fatal embrace with its star. The gravitational forces at play here are so immense that they are actively dragging the planet downward. Its orbital period is a frantic 0.94 Earth days, a blur of a year, and with each passing revolution, it spirals just a little bit closer to its own doom. This is orbital decay in action, a process we have long theorized but rarely witnessed with such clarity. The primary mechanism is tidal friction. Just as our moon's gravity gently tugs on Earth's oceans, the star's gravity exerts a colossal pull on the massive, close-orbiting planet. But because WASP-18b is tidally locked, always showing the same face to its star, the gravitational pull is not symmetrical. It distorts the planet's shape, creating a bulge, and the energy lost in this constant stretching and flexing saps the planet's orbital energy, causing its path to slowly but surely decay. Scientists estimate that at this rate, WASP-18b has perhaps only 1 million years left before it crosses the Roche limit, the point where the star's gravity will overpower the planet's own, tearing it apart into a spectacular ring of debris before the remains finally crash into the stellar surface. This introduces a terrifying timescale to planetary stability. We often think of solar systems as settled, permanent arrangements, but WASP-18b is a stark reminder that they are dynamic and sometimes violent. The extreme proximity and tidal forces also mean this world is being cooked from the inside out. The constant gravitational kneading generates intense internal heat, supplementing the already savage stellar radiation and ensuring its atmosphere is a forever churning cauldron of superheated gases, a place where no complex chemistry for life could ever hope to stabilize. This celestial countdown forces a profound question. If a giant 10-Jupiter mass world can be dragged to its destruction, what does that say for the long-term safety of smaller, rocky planets in tight orbits around their stars? Our search for permanently habitable worlds must now account for this invisible drag, this slow, gravitational siphon that can doom a world over cosmic timescales that are, for a planet like this, shockingly brief. From a world being torn apart by gravity, we turn to one that is barely held together at all, a cosmic wanderer with the heart of a comet. Fomalhaut b drifts through a celestial graveyard. Orbiting the brilliant star Fomalhaut just 25 light-years away, this enigmatic object is sheathed in a vast, luminous ring of dust and ice. It was one of the very first worlds ever directly seen in visible light, a tiny speck moving against the backdrop of its star's immense debris disk. But this is no serene, stable system. The planet, if it is a planet, carves a highly elliptical path that takes it on a wild swing from the calm outer, reaches directly through the densest, most dangerous parts of the circumstellar rubble. This journey is a gauntlet of intense radiation and countless collisions with icy and rocky particles, a place where any forming moon or developing atmosphere would be relentlessly pummeled. The environment is so chaotic that it challenges the very notion of a stable, life-friendly orbital neighborhood. The mystery deepens with the object's own nature. Some astronomers now question if Fomalhaut b is a solid planet at all. Its unusual brightness and behavior have led to theories that we might be looking at a colossal, expanding dust cloud, the aftermath of a cataclysmic collision between two protoplanets that occurred just before our telescopes turned to look. This would be a snapshot of planetary destruction, not construction. So what does this dusty chaos teach us? It is a window into our own solar system's violent past, a time billions of years ago when similar debris disks swirled around our young sun, and planetesimals constantly smashed together to build the worlds we know today. Fomalhaut b shows us that this process is messy, dangerous, and far from over in many parts of the galaxy. It forces us to wonder how any fragile, early life could survive such a bombardment. And just as we witness this world potentially shrouded in its own debris, we turn to another that is actively shedding its own substance into space, leaving a trail of its demise like a cosmic comet. GJ 436b presents a slow-motion unraveling, a world of ice caught in a stellar furnace. 33 light-years away, this Neptune-sized planet orbits a calm red dwarf, but its placid star belies a violent reality. The planet swings so close to its parent that its year lasts only 2.6 Earth days, bathing its atmosphere in intense radiation. This heat has created a bizarre paradox, an ice giant that is actively evaporating. The Hubble Space Telescope revealed its secret, a vast, comet-like tail of hydrogen gas streaming behind the planet for millions of kilometers. This is not a gentle leak, but a constant, powerful stellar wind stripping away the planet's outer layers. The core of GJ 436b is a mystery, likely rich in water, but the surface conditions are hellish. Any water vapor in the atmosphere is superheated, contributing to the Great Escape. Scientists estimate the planet is losing over 1,000 tons of hydrogen every second, a planetary hemorrhage that could leave behind a barren, rocky core in the distant future. This evaporation shatters the classic image of an ice giant as a cold, stable world in the outer reaches of a solar system. It proves that a planet's placement is everything, and even a giant can be vulnerable. How does this compare to other evaporating worlds like HD 209458b? Both are hot giants bleeding hydrogen, but GJ 436b is an ice-based world, suggesting that even planets born from different materials share a common fate when orbiting too close to their stars. This forces us to ask a chilling question. If a Neptune-sized world can be stripped to its core, what hope does a smaller, Earth-like planet have in a similar orbit? The relentless stellar winds from red dwarfs could easily scour away the atmospheres of any rocky worlds in their habitable zones, leaving behind airless, irradiated wastelands. GJ 436b is a monument to atmospheric fragility, a world slowly disassembling itself into the void. And just as we witness a world losing its atmosphere from a close orbit, we must now consider one whose entire path is askew, a planet that orbits at a dramatic and precarious angle. A world can be tilted so severely that its very poles become temporary tropics. HTP 7b, a gas giant over 1,040 light-years away, experiences climate chaos on a truly planetary scale. Its orbit is not a flat, tidy circle aligned with its star's equator. Instead, the path it traces through space is dramatically inclined, a steeply angled loop that subjects the planet to wild and unpredictable seasons. This profound tilt means that the star's most intense radiation batters first one hemisphere, then the other, as the planet completes its frantic two-day year. The result is a planet constantly struggling to balance its energy budget, with one side baking under stellar fury while the other plunges into a temporary, frigid darkness. This asymmetric heating does not create gentle breezes. It forges supersonic jet streams in the upper atmosphere, winds that scream across the globe at speeds of thousands of kilometers per hour. These are not localized storms, but permanent, planet-wide rivers of air, desperately trying to redistribute the overwhelming heat from the dayside to the nightside. Scientists first detected these ferocious winds not by seeing them directly, but by watching the clouds. Observations from the Kepler telescope revealed that the planet's brightest patches, believed to be colossal reflective clouds, were not stationary. They were being dragged across the sky by these invisible, high-speed atmospheric currents. The clouds themselves are likely not made of water vapor, but of corundum, the same mineral that forms rubies and sapphires. So this is a world where the sky races at unimaginable speeds, occasionally filling with clouds of vaporized gemstones. This bizarre configuration challenges everything we know about planetary migration. How did this world end up on such a skewed path? The most likely explanation involves a violent past, a gravitational tug of war with another, still unseen giant planet in the system that kicked HTP 7b into its current, unstable orbit. This tilted world forces us to confront a critical factor for habitability: axial and orbital stability. A planet can be the right size and the right distance from its star, but if its climate is subject to such violent and unpredictable shifts, any fragile ecosystem would be torn apart. The search for life requires not just a Goldilocks zone, but a Goldilocks orbit, a stable and gentle path that allows for a consistent and temperate climate. This extreme example makes our own Earth's steady tilt seem like a precious cosmic gift, a key ingredient that has allowed life to flourish for billions of years. From a world whose chaotic climate is written in its crooked path, we turn to one whose very substance is the stuff of legend, a planet that might be the ultimate treasure chest. Its very substance is a treasure, but its fate is a feast. WASP-12b is a world of carbon, a hot Jupiter so saturated with this fundamental element that it challenges the very chemistry we associate with planets. Located 1,400 light-years away, this gas giant orbits its star with such intimacy that a year passes in just over one Earth day. This proximity has sealed its doom through immense gravitational tides. The star's pull is so powerful it has stretched the planet from a sphere into a distinct egg shape, a celestial teardrop perpetually straining toward its devourer. This is not a stable relationship, but a slow act of consumption. The planet's outer atmosphere is being stripped away, siphoned by the star to form a hot, thin disk of accreting material. As this gas spirals inward, it superheats, causing the entire system to glow with an intense and deadly light. Yet the true marvel lies in the composition of this lost atmosphere. Spectroscopic analysis reveals a shocking lack of water vapor and a staggering overabundance of carbon-bearing molecules like carbon monoxide and methane. This is not an oxygen-rich world like Earth. It is a carbon empire. Under the immense pressures within the planet, this carbon could be crushed into vast strata of diamond and graphite, creating internal layers of glittering crystal. This carbon dominance shatters our Earth-centric view of planetary chemistry. We instinctively link habitability to water and oxygen, but WASP-12b presents a radical alternative. What if life could be based on a different biochemistry entirely, one that uses carbon chains in a methane-rich soup, utterly independent of water? While the surface of this world is a scorching hellscape, the concept it introduces is revolutionary. It forces us to ask if our search for life is biased by the singular example of our own planet. A carbon-rich world expands the palette of possible life-supporting environments, suggesting that biology could flourish in chemical contexts we would find utterly toxic. As we watch this world being consumed, we are reminded that the ingredients for life are universal, but the recipes may be infinitely varied. And just as we look into the carbon-soaked depths of one world, our gaze is drawn to another that mirrors the light with an almost metallic gleam. Kepler 10b offers a terrifying glimpse of a rocky world pushed to its absolute limit. 560 light-years away, this scorched planet completes a full orbit in less than one Earth day, racing around its star in a frantic, blistering dance. It was one of the very first rocky exoplanets we ever confirmed, a landmark discovery that proved small, dense worlds existed beyond our solar system. Its density is strikingly similar to Earth's, suggesting a composition of iron and rock that feels familiar. But that is where all familiarity ends. The planet's surface temperature soars beyond 1,300 degrees Celsius, a heat so intense it can liquefy granite. The entire sun-facing hemisphere is almost certainly a global ocean of incandescent lava, a churning, glowing sea of molten rock with no solid land in sight. This is not a landscape of volcanoes, but a single planetary-scale volcano. Any water, any atmosphere, any complex molecule would be instantly torn apart and vaporized by the stellar fury. Kepler 10b shatters the hopeful assumption that a rocky composition automatically means a habitable world. It defines the inner edge of what is possible for a terrestrial planet, a boundary of pure fire. Its existence forces us to ask where that line is drawn for other stars. How close is too close for a world to have any chance at all? The data from its transits, the tiny dip in starlight as it crosses its star's face, provides a crucial benchmark. It shows us how a rocky body behaves under extreme stellar bombardment, its surface relentlessly cooked and likely slowly evaporating over eons. This lava world is a lesson in extremes, proving that the habitable zone is not just a welcoming band of possibility, but a razor-thin ribbon flanked by infernos on one side and iceboxes on the other. From this realm of perpetual fire, we are drawn to an even more unstable environment, a planet not merely heated by a star, but orbiting the corpse of one. A pulsar's heartbeat marks the grave of a star. This is the environment of PSRB 1257 plus 12c, a world orbiting the corpse of a massive sun that long ago died in a supernova cataclysm. The pulsar itself is a city-sized cinder of ultra-dense matter, spinning hundreds of times every second and shooting out beams of intense radiation like a relentless cosmic lighthouse. Any planet near this remnant is bathed not in gentle sunlight, but in a perpetual, sterilizing deluge of X-rays and high-energy particles. This entire system, located 2,300 light-years away, was the first planetary system ever discovered beyond our own, a profound find that immediately shattered our expectations. We did not find it around a stable, sun-like star, but in this post-apocalyptic graveyard. The planets here, including PSRB 1257 plus 12c, could not be the original worlds of the dead star. They are almost certainly second-generation orphans, formed from the shattered remains of the progenitor star and its original planets, a disk of debris that coalesced anew from the ashes of destruction. This forces a radical rethinking of planetary formation. It proves that planet building is not a gentle process confined to stellar nurseries, but a tenacious force that can emerge even from total stellar annihilation. How could anything survive in such a place? The surface of this planet would be scoured clean by radiation, its rocks likely made radioactive, its entire structure cooked by the pulsar's furious energy output. The concept of a surface is itself questionable, as the world might be a barren, metallic core stripped of any volatile elements. This dead system raises a haunting question about the resilience of life. If biology could somehow take hold in the absolute worst conditions the universe has to offer, where could it not thrive? While this particular world is a radiation-blasted hellscape, its very existence expands the possible windows for life to unimaginable extremes, perhaps deep underground where the rock provides a shield. PSRB 1257 plus 12c stands as a monument to cosmic rebirth, a world born from death, challenging us to look for life not just in the gentle places but in the ruins. From this frantic, irradiated cinder, we now journey to the profound stillness of a world where a single year spans epochs. While pulsar worlds race through their frantic orbits, another planet moves with the patience of a glacier. Piscium b is a distant giant whose single year spans 160,000 Earth years. This colossal time frame means the last time this world was in its current position, our own species, Homo sapiens, was just beginning to spread across the globe. Located 155 light-years away, this gas giant orbits its parent star at a staggering distance, hundreds of times farther than Earth is from our Sun. It exists in a realm of near absolute zero and profound darkness, a frozen wanderer in the outer void. Its discovery was a feat of direct imaging, a tiny pinprick of infrared light against the blackness, its own faint heat signature betraying its presence. This immense separation shatters our conventional models of how gas giants form. The core accretion theory struggles to explain how a planet can accumulate so much gas so far from the warmth and material of its star. This suggests that some worlds may be flung outward by gravitational interactions, becoming permanent exiles in their own solar systems. The atmosphere of Piscium b would be a study in deep freeze. With minimal stellar heating, its outer layers are likely a frozen shell, with gases like methane and ammonia condensing into icy crystals that fall as slow, perpetual snow. The internal heat left over from its formation might be the only thing preventing it from becoming a completely solid ball of ice. But what about the possibility of life here? The planet itself is a hydrogen-rich icebox, utterly hostile. However, the potential for large, warm moons orbiting this giant is a tantalizing thought. Heated by the immense tidal forces of the planet's gravity, such a moon could maintain a subsurface ocean of liquid water, sealed beneath a thick crust of ice. Life in that abyssal darkness would be completely cut off from the universe, relying on geothermal vents for energy, never knowing the sun that shines faintly billions of kilometers away. This distant world proves that the conditions for life are not always about proximity to a star, but can also be generated by the gravitational dynamics of the planets themselves. It expands the habitable zone from a narrow stellar band to the entire expanse of a solar system. Yet, the profound stillness of this frozen realm stands in stark contrast to our next world, where the atmosphere itself is a chemical powder keg, capable of sudden and violent transformation. A world can be rich with the ingredients of life, yet utterly hostile to life itself. HTP 11b, a Neptune-sized world 124 light-years away, presents this exact paradox. Its atmosphere is a chemical laboratory, surprisingly clear of obscuring clouds, allowing our telescopes a rare, direct look into its composition. And what they found was a landmark discovery: water vapor. This was one of the very first confirmations of water in an exoplanet's atmosphere, a moment that electrified the search for habitable worlds. But this is not a gentle, watery world like Earth. Planet orbits so close to its star that its surface temperature soars to a blistering 500 degrees Celsius. There is no solid surface, only a gradual descent into a hot, dense fluid core. The water here is not pooled in oceans but is a superheated gas, part of a churning, alien atmospheric soup. Even more intriguing is the presence of another molecule detected alongside the water: methane. On Earth, methane is a potent greenhouse gas, but it is also a key organic molecule, often associated with biological processes like those in swamps or the digestive systems of animals. Finding these two substances together on a distant world is a profound clue, a snapshot of complex chemistry playing out under extreme conditions. This combination forces us to refine our models of atmospheric science. How do these molecules interact and persist in such a hot, turbulent environment? The processes are likely driven by intense heat and pressure, far from any biological activity, yet they produce the very building blocks that, in the right context, could lead to life. This is the crucial distinction HTP 11b teaches us. The presence of water and organic molecules is not a biosignature, not proof of life. It is a potential signpost, a chemical prerequisite. It tells us that the fundamental ingredients for biology are being forged and scattered throughout the galaxy, even in the most unlikely of places. This discovery guides our entire search strategy, training our most powerful telescopes to look for these molecular patterns in the atmospheres of smaller, cooler, rocky worlds. If we find this same combination on a planet in the habitable zone, the implications would be staggering. So while HTP 11b itself is a scorching giant, its clear, chemically rich air acts as a beacon, showing us what to look for as we scan the cosmos for worlds that are not just habitable, but perhaps even inhabited. This glimpse into a mature world's atmospheric recipe makes the next discovery even more startling, a planet so young it has not yet finished assembling itself. A planetary system is not born in an instant, but forged over millions of years in a swirling cradle of dust and gas. LkCa 15b is a rare and breathtaking snapshot of this very process, a gas giant caught in the act of being born. 473 light-years away, this young world orbits within a distinct gap in its star's vast, pancake-shaped protoplanetary disk. We are not looking at a finished product, but at a cosmic construction site. The planet itself is likely still accumulating mass, pulling in streams of gas and dust from the surrounding disk, growing even as we observe it. This active accretion generates intense heat, causing the infant world to glow with a fierce, ruddy light. The environment is one of unimaginable chaos and violence, with planetesimals constantly colliding, and the potential for new moons to coalesce from the debris circling the giant. This direct observation shatters the idea of planetary formation as a neat, orderly event that happened long ago and is now complete. It reveals that solar systems can remain active, turbulent nurseries for eons, with worlds assembling and rearranging themselves in a dynamic dance. This forces a profound question about our own origins. How did the Earth and its sibling planets look during their own first few million years? The chaotic environment around LkCa 15b suggests that the early solar system was a far more violent and unpredictable place than we can easily comprehend, with giant planets carving gaps and scattering debris, their gravitational influences dictating the fates of smaller, rocky worlds still forming farther out. The youth of this world informs us that the path to a stable, habitable planet like our own is a gauntlet, a journey through a period of intense bombardment and orbital instability. For life to eventually emerge, a world must first survive its own violent infancy. This glimpse into planetary birth makes the strange fate of fully formed worlds seem even more dramatic, especially one whose very shape is being relentlessly sculpted by an unforgiving star. Gravity sculpts this world into a cosmic rugby ball. WASP 103b is a hot Jupiter stretched thin by its star, a planet enduring a constant, brutal tug of war. 1,800 light-years away, this gas giant completes an orbit in less than a single Earth day, locked in a proximity so tight the star's gravity does not merely pull, it distorts. The immense tidal forces have yanked the planet's sphere into a distinct oval shape, creating two massive bulges, one perpetually facing the star and the other pointing directly away. This is not a static form, but a world in constant, painful flux, its very structure flexing with each frantic revolution. The energy dissipated by this endless stretching generates intense internal heat, supplementing the already savage stellar radiation and turning the planet's interior into a churning furnace. This tidal heating has profound consequences that reach far beyond the planet itself. If WASP 103b were to have moons, their fate would be grim. The same gravitational forces distorting the planet would relentlessly knead any orbiting bodies, likely triggering worldwide volcanic eruptions that would shatter their surfaces and boil away any nascent atmospheres. This reveals a hidden layer of instability within solar systems. A planet can be the right size and distance, but if its gravitational interactions are too severe, it can become an engine of destruction for any smaller, potentially habitable worlds in its vicinity. The distorted form of WASP 103b forces us to measure habitability not just in light years from a star, but in the subtle, invisible tensions between celestial bodies. It shows us that gravity is a sculptor and its art can be violently inhospitable. Yet, as we witness a world warped by external forces, our search turns to one whose own atmosphere acts as a perfect mirror, a planet cloaked in metallic clouds. Co-Rho T7b is a world of absolute extremes, a rocky planet split into two permanent and terrifying realms. Located 489 light-years away, this super-Earth is tidally locked to its star, meaning one hemisphere forever faces the stellar furnace while the other is cast into endless night. The dayside is a vision of pure hell, with temperatures soaring to 2,500 degrees Celsius. This is a heat so intense it does not merely melt rock, it vaporizes it, creating a thin, tenuous atmosphere of vaporized stone. The surface below is almost certainly a global ocean of incandescent lava, a churning, glowing sea where continents cannot form and solid ground is an impossibility. This is the ultimate expression of a planet pushed to its thermal limit. Yet, cross the Terminator line into the perpetual darkness of the night side, and you find a cold so profound it defies earthly comparison. With no star to warm it, temperatures here plummet to hundreds of degrees below zero. In this deep freeze, the very minerals vaporized on the dayside, elements like sodium and potassium, are able to condense. They would fall from the black sky not as water flakes, but as a fine, metallic snow, dusting the frozen, rocky landscape in a glittering, toxic frost. This stark dichotomy shatters the hopeful notion of a gentle twilight zone. The colossal temperature difference between these two hemispheres would not create a stable, temperate band. Instead, it would generate hurricane-force winds, a supersonic atmospheric river screaming from the hot side to the cold, carrying vaporized rock that then freezes and falls as that bizarre mineral precipitation. Any hope for a sliver of habitable real estate is torn apart by this violent global weather system. Co-Rho T7b teaches us that a rocky composition and the right location are not enough. The planetary environment itself must be stable, and this world is a perpetual storm of fire and ice, proving that some worlds are simply too geologically active and climatically chaotic to ever support life. This relentless stellar fury hints at an even more dramatic future, for the star Co-Rho T7b orbits is aging, destined to swell into a red giant and utterly consume this world of two extremes. A world watched its own sun die and lived to tell the tale. V391 Pegasi b is a cosmic survivor, a gas giant orbiting the stellar ghost of a red giant star 4,570 light-years away. Billions of years ago, this planet's star began to swell, blasting out immense heat and radiation as it transformed into a red giant. In any inner solar system, this is an apocalypse. The star's outer layers expand to engulf and vaporize any worlds orbiting too close, a fate that awaits Mercury, Venus, and likely Earth when our own sun reaches this violent stage in its old age. Yet V391 Pegasi b, orbiting at a much greater distance, endured the inferno. It witnessed its star swell to a colossal size, then violently shed its outer layers, collapsing back into a hot, dense ember known as a subdwarf. The planet now orbits this stellar corpse, a testament to resilience in a radically transformed system. Its very existence shatters earlier predictions that such planetary systems would be completely torn apart by the death throes of their stars. It proves that some worlds can persist, migrating to new, stable orbits as their star goes through its final, dramatic acts. But survival does not mean habitability. The environment around this subdwarf is one of intense ultraviolet radiation and a history of blistering heat, a far cry from the gentle, steady warmth we associate with life. This forces us to confront the ultimate transience of habitable zones. The comfortable belt around a star where liquid water can exist is not a permanent fixture. It is a moving target, a window of opportunity that opens and closes over billions of years. V391 Pegasi b offers us a preview of our own solar system's distant future, showing that while planets might endure stellar death, the conditions for life are fleeting. This glimpse into a system reshaped by stellar evolution makes the chaotic dance of a planet in a binary system seem all the more precarious. The sky above HD 188,753 AB holds not one, not two, but three separate suns. This world, 149 light-years away, is a marvel of celestial complexity, orbiting within a triple star system that defies our simple models of day and night. The planet itself is a gas giant, tightly bound to the primary star of the system, while that star is itself locked in a close dance with a second stellar partner. A third, more distant star orbits this central pair, creating a gravitational web of immense intricacy. The potential for orbital chaos is ever present, as the competing pulls of three massive bodies could easily destabilize the path of any smaller world or moon. For a planet in this system, the concept of a stable, circular habitable zone dissolves into a shimmering mirage. The amount of radiation bathing the world would fluctuate wildly, depending on which stars were dominant in the sky at any given moment. There could be periods of triple daylight, bathing the planet in intense, multi-directional heat, followed by times when only one star is visible, creating a temporary and deceptive calm. This constant shift would forge a climate of unimaginable turbulence, with temperatures swinging between extremes and global weather patterns thrown into perpetual upheaval. How could life find a footing in such an environment? Any potential biology would need to withstand not just seasonal change, but radical climatic shifts dictated by the slow, grand orbital cycles of the three stars. This stellar triad forces us to expand our search for life into ever more dynamic and complex systems, where stability is not a permanent state but a fleeting, precarious balance. It is a stark reminder that our own single, steady sun is a cosmic luxury, not a universal standard. Such complex gravitational forces can exert a profound influence on a planet's very orientation, setting the stage for a world whose tilt throws it into a perpetual state of violent seasonal rebellion. Kepler 413b takes unpredictability to a cosmic extreme, a world whose very orientation in space is constantly shifting. This super-Neptune, located 2,300 light-years away, orbits a pair of closely dancing stars, but its path is far from stable. The planet's entire orbit is precessing, meaning the axis around which it orbits is itself slowly rotating, like a wobbling spinning top. This motion causes the planet's axial tilt, the angle that gives a world its seasons, to change dramatically over a cycle of just 11 years. Earth's stable tilt of 23.5 degrees gives us reliable, predictable seasons, but on Kepler 413b, the tilt can vary wildly, leading to a climate of pure chaos. For any potential moon orbiting this giant, the results would be catastrophic. Seasons would not follow a gentle annual rhythm. They would be erratic and extreme, swinging from periods of endless, scorching summer to epochs of deep, global winter without warning. The concept of a stable climate, a cornerstone for the evolution of complex life, simply vanishes. This constant wobble forces us to confront a subtle but devastating factor in the search for habitable worlds. A planet can be the right size, the right distance, and even have water, but if its spin is unstable, any fledgling ecosystem would be wiped out by the relentless climatic shifts. This processing world asks us how life could ever gain a foothold in an environment that is constantly redefining its own rules. As we reach the end of our journey through these 25 bizarre worlds, a profound pattern emerges. From diamond planets to worlds of sideways glass rain, from puffy giants to wobbling orbits, each one shatters a different assumption about what makes a world livable. They teach us that habitability is not a simple checklist of water and air. It is a delicate, dynamic balance of geology, chemistry, orbital mechanics, and stellar relationships. Our own Earth is not just a lucky planet in a gentle zone. It is a rare gem of stability in a cosmos filled with chaos, a world that has maintained its delicate equilibrium for billions of years. The true lesson of these alien worlds is not that life is impossible elsewhere, but that it could be hiding in forms and places we are only beginning to imagine. The universe is far more creative and violent than we ever dreamed, and our search for life must now expand to include the strange, the unstable, and the utterly alien. The definition of a living world is no longer just another Earth. It is any world where chemistry and energy conspire to create something new, and our journey to find it has only just begun. These 25 worlds have not just expanded our catalogue of planets, they have fundamentally rewritten the rules for life itself. Our Earth-centric checklist for habitability, with its requirements for liquid water, moderate temperatures, and a stable orbit, now seems hopelessly narrow. The universe is showing us that life, if it exists out there, is likely far more stubborn and inventive than we ever presumed. Consider the extremophiles right here on Earth, thriving in places we once thought sterile. Microscopic life forms flourish in the boiling, acidic waters of hot springs and cluster around superheated vents in the lightless ocean depths, sustained entirely by chemical energy from the planet's core. If life can persist in these terrestrial hellscapes, then why not in the scalding, global ocean of GJ 1214b, or deep within a tidally heated moon orbiting a puffy giant like Kepler 7b? The environments we once dismissed as lethal may merely be challenging, presenting a different set of puzzles for biology to solve. This forces a dramatic shift in our search strategy. We can no longer only look for planets that mirror our own. Instead, we must train our telescopes to detect a broader palette of biosignatures. An atmosphere rich in methane and other complex hydrocarbons, like that of WASP-12b, could indicate a novel carbon-based biochemistry. Unusual thermal patterns on a tidally locked world might reveal geothermal activity powering a subsurface ecosystem. The goal is to recognize the chemical signatures of life, even if that life operates under rules we have yet to imagine. How do we design missions and instruments capable of sensing these alien indicators? The next generation of telescopes will need to be exquisitely sensitive to a wider range of atmospheric gases and surface conditions, looking for imbalance and complexity rather than just the familiar trio of oxygen, carbon dioxide, and water vapor. This expanded perspective turns the entire cosmos into a more promising hunting ground, where every bizarre world becomes a potential cradle for something new. Our journey through these 25 planets is not an end, but a new beginning, pointing our gaze toward a future of discovery that is stranger and more wonderful than we ever dared to dream. Our tour of these 25 alien worlds reveals a cosmos of breathtaking diversity and relentless creativity. We have witnessed planets of diamond and sideways glass rain, puffy giants lighter than styrofoam, and worlds actively evaporating into space. Each one dismantles a piece of our old, Earth-centric definition of a habitable world. They prove that the universe does not play by our limited rules, and life, if it exists, is likely a master of adaptation, thriving in conditions we would consider absolute hell. The next generation of telescopes, like the James Webb Space Telescope, will peer deeper into the atmospheres of these strange worlds, not just to find another Earth, but to discover entirely new categories of chemistry and climate. We may soon learn that life is not a rare and delicate phenomenon, but a tenacious force that can emerge in the most unexpected places, from the scalding depths of a water world to the tidally heated core of a distant moon. Which of these bizarre exoplanets captured your imagination the most? Was it the Diamond World 55 Cancri E, or the eternal hurricane of HD 189,733b? Share your thoughts in the comments below. If you enjoyed this journey to the edge of cosmic possibility, be sure to subscribe for more explorations into the mysteries of space. Keep looking up, for the universe is a place of infinite wonder, and its greatest surprises are still waiting to be found.